I'm going to present the paper that is called 3D Infomax Improved GNNs for Molecular Property Prediction, which came out of this awesome collaboration with a bunch of awesome people. And if I don't realize you're raising your hands, but Michael Sedong, I think, is just raising his hand to try it out. If I don't realize you're raising your hand later on, then just feel free to interrupt me. But yeah, if you actually have a question to the people who are raising their hand right now, then just go ahead. But then I will start. Yeah, so we know that if we want to do some molecular property predictions, we can do that quite well if we use GNNs and represent our molecule as a graph. So maybe this is the type of audience who already knows this, but I'm still going to go over it very quickly. We can represent a molecule as a graph where we have the atoms as nodes and the edges are the bonds between the atoms. Yeah, and then if we have a molecule represented as a graph like that, then we can just use some sort of GNN, some graph neural network to process, do some message passing on the graph and end up with node embeddings, node features, and those we can pool to a single representation vector maybe, and then predict some properties of the molecule. And we know that that works quite well if we represent our molecules and use our molecules like that. But we also know that we can make much better predictions if we additionally use the 3D information of a molecule. And what I mean with 3D information is just the individual 3D coordinates. So, and throughout the talk, I will refer to 2D information. Basically, I will refer to everything other than 3D information as 2D information. So I just mean the molecular graph with 2D information and the features, the edge features. Yeah, and with 3D information, I just mean the possible conformers that the molecule can end up in. Yeah, and then we can get some much nicer property predictions if we use the 2D information together with the 3D information with some 3D GNN, like for example, DimeNet, eGNN, or spherical message passing, if those already tell you something. Okay, so we know that 3D information is very nice to make better property predictions, but we also know that this 3D information is sometimes not so easy to obtain. So for many molecules, maybe we can even say for most molecules, we are not aware of the 3D structure, and we can often computationally determine it with some quantum simulations, but doing that can take a long time. And if we want to process a lot of molecules, then this becomes computationally problematic. Yeah, so we basically now have this situation here on the left, where we have a bunch of down here we have a bunch of molecules for which we know the 2D structure or the 2D information, just the molecule itself, and we know the coordinates of the atoms. So we have a few of those where we do know the 3D information. But for a lot of other molecules, we only have the 2D molecular graph, and maybe those are exactly the ones for which we do want to predict the properties. Yeah, and what we can do is to just use the 2D graph, as we said before, some GNN, get node representations, and then predict the property. And of course, this is very fast because we can process a lot of molecules in parallel with the GNN just in batches, and just need to do a single forward pass to get many property predictions at once. But so this way we are of course stuck with the 2D level of accuracy, and we cannot leverage any 3D information about the molecule. But we have the opportunity to calculate some 3D information, as we said before, with some quantum mechanical simulations. And then we can use this 3D information as additional input to some 3D graph neural network to get our more accurate property predictions. But this is, of course, very slow. These sort of or well, it depends on the level of accuracy that you want to get, but these property or these methods can be very slow, these quantum mechanical simulations, if we want to get very accurate conformers. And then other thing that we could do is use some learned methods to explicitly generate the 3D information. And while there has been some very impressive progress there this year with papers, or last year by now, with papers like GeoMol or learning gradient fields for molecular conformation generation, these methods are sometimes even a bit slow, and the conformers that they generate can, yeah, they're definitely not at the level of conformers that we can generate with some quantum mechanical simulations if we have enough time. Okay, but then what is our idea? How do we want to address this? Well, we say we don't generate some explicit 3D information, like here with this graph, this neural network that just produces some explicit 3D coordinates, some concrete conformer. Instead, we say we want to train a network to produce latent 3D information. So this is the thing that we quickly depicted over here. So right in the beginning, we have our bunch of data for which we do know the 3D information. And the idea is to use that to pre-train some 2D graph neural network. And I will get into how we do that, this pre-training step. Yeah, but we want to pre-train this network to capture some 3D information. And then we can transfer the weights of this network to over here and use it to predict, or use it with the molecules for which we only know the 2D information, right? And the training data during pre-training is the data for which we know the 3D information, but then we can later on transfer the weights and use the weights on molecules for which we only have 2D information available. Yeah, but now quickly into this pre-training step, this mutual information maximization. Well, what we have here is this 2D network generates some latent 3D information, and this 3D network encodes the 3D information also just into a single vector. And then we say we want to maximize the mutual information, to sort of make those vectors similar, with the idea that, well, then this vector will have to carry some 3D information, and the 2D network will have had to learn to generate this 3D information just from the 2D inputs. Yeah, and after it has learned this, we transfer its weights. We take the 2D graphs for which we don't know the 3D information, but the 2D network is still able to produce some latent 3D information from just those 2D inputs. And this latent 3D information we can then use to make more accurate property predictions. And while they are more accurate, we're still just as fast as whatever regular GNN you have here. And we just need to do our forward pass and are able to use some degree of latent 3D information. Okay, of course, we're not able to use as much 3D information as if we had the true conformers, but it improves the accuracy of the property predictions. But then, whoops, let's get, let me go back. Right. Let's get into
maybe
Clemens?
the first actual question. When you try to maximize the mutual information between the 3D and 3D maps, do you only update the weights in the 2D map after like some pre-training step in the 3D map? Or because that seems like something where the 3D net might also be incentivized to just extract 2D information. Right?
Yeah, sorry, you're a little bit hard to understand, but maybe just confirm of what you're asking is, if we maximize the mutual information, we might run into the problem that we don't learn to encode 3D information here, but actually we just learn, the 3D network just learns to encode 2D information over here.
Yeah, exactly. Sorry for the microphone quality.
Yeah, no problem. But that's exactly the right question. And that's something we have to address and look into, and one of the main concerns, but we'll get into that later.
Just a comment, in theory, if you maximize mutual information, this should not happen, because that means you're trying to maximize the amount of information you extract from the 3D net as well. There would be less bits. If you throw away information from the 3D thing, then the mutual information will be smaller.
Yes, but well, yeah, but why? Okay, the 3D information will be smaller, but isn't it still the case that, well, we're able to better, or the 3D information that we're encoding is higher if we prevent the 3D network from just encoding 2D information. So if we have for example, the features, the node features here, and we just encode the node features here, and we have some objective to maximize the mutual information with contrastive learning, and then during the contrastive learning, we're able to perfectly distinguish each vector just based on the node features, then we wouldn't have to capture any 3D information here, right?
No, but then the mutual information would not be maximized.
Yeah, okay. Then
so I'm just saying, maximizing mutual information is not easy, and maybe the method that you're using is not doing the best possible job. But if you are really maximizing mutual information,
okay,
then that problem should go away.
Good. So the real mutual information maximization wouldn't have that problem, but the method that we will use to approximate that will have the problem, I think. But then let's actually get into how can we do this? What is one way to pre-train our network? Well, what we could do is to train this GNN to capture some latent 3D, or to generate some latent 3D information, is to just pre-train it by directly generating some conformers. Well, and this is kind of an obvious idea. Like, for example, we just predict all of the pairwise atom distances, and then we hope that the GNN will have learned to generate some 3D information in its latent representations, because otherwise it wouldn't be able to accurately predict the distances. And this is maybe an obvious baseline that we will also look at later. But how we actually do it is with this mutual information maximization approach. And now we just do that with contrastive learning, and maybe the standard approach, if you want to say that. And to quickly explain that, so just as a quick contrastive learning introduction, we now have this 2D vector that we're generating here and the 3D vector that we're generating over here, and we want to kind of maximize the similarity between them such that we know we have some 3D information over here, because, well, we have 3D information over here, and to have a high similarity, then the 2D network also has to generate some 3D information just from the 2D inputs. And as a notion of similarity, we can just see the cosine similarity. But if we were to really just now maximize the cosine similarity, then we would have the problem that we could, for example, perfectly solve this objective by completely ignoring our inputs, and, well, the 2D network just produces a vector of constant 2's, and the 3D network just produces a vector of constant 2's no matter what we have as input. Then we have 2's here, 2's here. It's perfectly similar. The cosine similarity will be 1, and it is maximized. And this would, of course, not be useful. So what we do in the intuitive explanation of contrastive learning is that we consider some negative examples. Well, what do I mean with that? Let's just look at this example. This example right here, where we have a batch of 3 molecules with the 2D molecular graph on the left here, and the corresponding 3D information is always on the right. And yeah, we also again just put this to our 2D network, to our 3D network to produce our 2D and 3D representations. And then as before, we say we want to have a high similarity between the 2D representation and the 3D representation if they belong to the same molecule. So here the light blue molecule. But we additionally say that we want to have a low similarity if the 2D representation belongs to another molecule than the 3D representation. And this can kind of be nicely captured in this, in this loss term, which you might be familiar with in contrastive learning. Okay, but then we previously said that a single molecule can not only have a single 3D representation. So here we just have a single molecule and a single 3D conformer. But we know that actually a molecule can have multiple plausible 3D configurations. So yeah, here, maybe this molecule has these two plausible 3D configurations, and this molecule has these two plausible 3D configurations. And if we now want to include the information of multiple conformers, and therefore the possibility of different interactions or different properties that the molecule can have, then we also have an approach to do that. But let's maybe first get to the question from Clemens, unless you're no longer, unless you're still raising your hand from before. And maybe let's start with the question from Professor Bengio.
Thanks. So two things. One is, one of the issues with these contrastive methods is the negative examples. Like, you can see that if you don't choose your negative examples sufficiently close to the positive examples, then it may just be happy with some features that make it easy to distinguish from most negative examples. And so, you know, as soon as it finds something that matches between the 2D and the 3D, it might become harder to find more features. The other question I have is, have you tried, instead of the contrastive methods, just predict the 3D information from the 2D information? That would not suffer from that problem.
What do you mean with predict the 3D information? So for example, predicting pairwise distances?
Whatever. I mean, I understand you have these conformations, so you have to think of it like a distribution over 3D conformation. So you have to represent that in some way and then predict that distribution by maximum likelihood or whatever else.
Yeah, so we, for example, there are different methods for molecular conformation generation where we try to produce some conformers, and they most of the time also contain some graph neural network, and we tried two of those approaches to pre-train the graph neural network.
But what I'm saying is it could be an alternative to the mutual information approach, which would not be sensitive to the issue of choosing negative examples. Now, the challenge becomes to represent the generative distribution over conformations, and now you're going to make that distribution conditional on the representation of the 2D net.
Ah, okay. So you mean we generate some vector here, and this is now the additional input to some molecular conformation generation approach that just also goes from the 2D graph to some conformer?
No. Let's say you have a generative model, like say something like a GAN or VAE or some other generative model, or a GFlowNet, that can generate a distribution over conformations.
Okay.
Okay, so it's some kind of neural net that can do that, right? Now you can make that neural net conditional, so it has an input that is your Z from 2D representation. And then you train the whole thing end to end. So given the 2D representation, you maximize the likelihood of producing the conformations that you know exist for that molecule.
Yeah, but that's kind of what we're doing, right? If we have, for example,
that's kind of if mutual information was maximized, but there's the issue of finding the negative examples.
No, I mean, if we have some, if we have a model like GeoMol, if you're aware of it, where we are generating, where we have these, we are generating a distribution of conformers, and yeah, we're also, let me draw a little bit, like we have this molecular graph here, and then we have our GNN that gives us a bunch of node representations. And those node representations can now be seen as this latent vector, right? And this latent vector is then used by some generative model to, or these latent vectors are then used by the generative model to generate, I don't know, 10 different 3D conformers.
Yes, that's what I'm saying.
Yeah, that's what we use as one baseline, and that's
Okay.
what we call conf-gen as our baseline.
All right.
Get into the later. But another excellent point of the that you brought up is this problem of hard negative examples, which might be especially a problem here because, well, what if our 2D network and our 3D network, or produce representations here where we're able to just distinguish the molecules based on the number of atoms here. Like, what if we just count the number of atoms in our graphs? And what we can do to avoid that is, for example, sample batches where the number of atoms is always similar or the same or something like that.
Yeah, but if it's not number of atoms, it could be some other feature that you don't know that it's exploiting that makes it easy to distinguish positive and negative, and then that objective is maximized. And it's hard. I mean, in theory, if you had an infinite sum in the denominator, then it would be fine, but you don't, and that's the problem.
Yeah.
All right, thanks.
Thanks for the comments. But then to Cas.
Yeah, I was wondering, it's about the next slide. In the case where you have multiple conformers, I can imagine that a molecular property depends on one particular conformer, or maybe a subset of. And I'm not entirely sure. I think not, that you cannot, I feel like you cannot capture information about a particular conformer with this approach, but rather you kind of learned the shared information between the different conformers.
Yeah.
So would that be like a bottleneck or something that limits the maximum performance you can get?
Well, we can't, if we just have the 2D input, we can't make any conformer-specific predictions, right? Any conformer-specific property predictions. What the thing that we gain by looking at multiple conformers is if maybe this conformer has one property and this conformer has another property, then we now have the ability for this 2D network to learn that this molecule can have either this or this property. Yeah, like it's a bit vague, but I think I understand.
I think I understand what you're saying, but I was just wondering, because you considered them both as a positive, like I'll just leave it here because I need to think about this as well. But I was just wondering.
I think it works. It works, Cass. So think of it like it's going to say yes for any of the confirmations that are correct, and it's going to say no to confirmations that don't match the 2D structure. So that's just, that binary classification problem, which is what this likelihood thing is doing in principle the good job here, even if you have many confirmations.
But are you then still able to leverage information from one particular conformer? Yeah, maybe. Okay.
No, it's just trying to find, is this 2D structure possibly going to be associated with this confirmation? But it can also say yes to some other confirmation. They are not mutually exclusive.
One question that I have here is, how do you account for the fact that maybe some conformers are more prevalent than others? because yes, it's good to say yes to different conformers, but the reality is that maybe some of the conformers have like are those that represent the most of the time the way the molecule behave, and some are just don't that are not that prevalent. So how do you account for that?
So first of all, we look at the top K conformers, and then we tried like the top K most probable conformers, and then we tried stuff like weighting them and or sampling them, the most probable ones more often than the less probable ones. But in the end, this didn't really give any empirical differences, and we just went with using the top K conformers in a batch. And if we only had one, if we only knew about one conformer, then we just repeated that one conformer K times. Okay.
A suggestion?
A suggestion?
Yes. Would you be able to train on the energy at the same time as the conformation? Because what you really want to learn is the distribution of the conformations relative to their energy, because that's what you would do in a Boltzmann weighted average, which gives you general properties of bulk sample.
So yeah, what you're saying is that, for example, the 3D network now additionally outputs a number that is the energy.
Yes, the relative energy to the lowest energy conformation, really.
Okay, but yeah, that's we kind of would want this. We want to pre-train our 2D network, right? So we kind of would have to predict our.
The same way the 2D network gives you a distribution of conformations, it should also give you a distribution of energies.
Yeah, but right now we don't actually generate a distribution of well, okay, we could then go ahead, take this representation and have some generative model on top of it, or use this as conditioning on.
I think we are not seeing your drawings anymore.
Okay. I'm seeing them on my other screen. Cast, does it work for you? Okay.
Yeah, I still see them.
Okay.
Yeah. Okay, but yeah, maybe that's an idea that we have another generative model on top of that that tells us about the distribution of the conformers that we have over here, like the energies of the different conformers over here. But I now have no concrete idea how I would do that straight away.
Hannes, just to jump in here,
yeah.
One simple solution would be that the 3D network learns its own energy from its 3D conformation, and implicitly, by maximizing the mutual information, the 2D network will capture this information as well. But if I'm not mistaken, I thought like we had a similar idea in the project. Did we do that as well, or not really?
A similar idea?
I think I remembered we did pre-train only on the energy, and it didn't give as good results. But I don't think we did we ever try to predict, to both maximize the mutual information and predict the energy at the same time, or this is not something? No,
we didn't. Yeah, but what Dominique is saying, that, well, we can just and I was wrong in saying that before. What we can just do is to generate the 3D conformers, the 3D vectors, and from those 3D vectors we predict the energies of each of them. Like here, the energy of this conformer, and then because we maximize the mutual information, we still will have this information somehow over here, right? Okay, but then sorry, Emmanuel, but maybe we should keep going a little bit, and then if the time is good, then I will get back to your question, right? Good, but then we already, let me say it like this. we now have this 2D network, which is an arbitrary GNN that we want to pre-train, and we have this 3D network. So what can this 3D network be? Well, we wanted to satisfy some nice properties if we work with 3D molecular representations, and that is, well, ideally it should capture the full geometry of the molecule. It should be translation and rotation invariant, and what I mean is just if we have a molecule, we move it in space or we rotate it, right, then the properties stay the same. So we want it to be invariant with respect to that. And yeah, we actually don't want it to be reflection invariant because molecules have chirality, and the properties of molecules, at least if they interact with other molecules or if the properties depend on interaction with other molecules, they can change depending on the chirality or the handedness of the molecule. So what we could do, for example, and there are a bunch of different architectures that can operate on the 3D representations of molecules. And one of them is, for example, this equivariant graph neural networks, where we okay, now one thing that we can do to quickly say it is that we just look at all of the pairwise distances, right? And if we look at all of the pairwise distances between the atoms, then we capture the full geometry up to rotations and translations. And if I'm saying up to translations and rotations, we already know that we have this translation and rotation invariance, because, well, the distances, of course, don't change if we rotate or translate the molecule. Good, and maybe we can get into these 3D GNNs in a bit more detail later, but let's now get to some tests and some results in the next 5 minutes, because what we have, or what we're doing here, right, is we need some data sets with 3D information to do our pre-training step, and then we want to evaluate our models on only 2D information and predict some properties and see if, well, did we maybe predict the properties better than if we had used the same network in an unpre-trained or non-pre-trained state. And we take these 3 data sets with 3D information. QMax, thank you, Clemens Isat. Well, this QM9, for example, is just a data set where we have just the molecules and 3D information, and similar for these others. And yeah, we take 1/2 of QM9 to do this pre-training right here. And then we take the second half of QM9, like a disjoint half of QM9, and act as if we didn't know the 3D information of those molecules, and then use them as input here and predict some quantum properties of the QM9 molecules. And the same we can also do with 1/2 of geom drugs, which is just another data set like that. Okay, but then let's look at some result numbers. And what we have in this table is the mean average error. Like here, a bunch of mean average errors that we're getting when predicting these properties of 1/2 of the QM9 data set. And yeah, here is the mean average errors that we're getting if we're doing no pre-training, like just using the GNN and the vanilla GNN and predicting the properties. And here are the numbers that we're getting if we do our pre-training on with either 1/2 of the QM9 dataset, or with the geom drugs dataset, or the QMax dataset. And yeah, over here we have some different contrastive pre-training baselines that don't use 3D information, but also use some other objectives for self-supervised pre-training of graph neural networks. And then here we have a column where we're just generating conformers with RDKit, which is, we can generate some conformers that have less accuracy than the highly accurate quantum simulation conformers, but they're much faster to generate. And then we use the 3D GNN circle message passing to generate or to predict the properties using this 3D information as additional input. And then lastly, what we have here is if we use the true or the ground truth 3D conformers to predict the properties with the 3D GNN circle message passing. And this is then basically the limit, or as good as we could get. But we can see that we won't reach this limit, but we're getting closer to it than this baseline. Because we see that if we, for example, look at the numbers that we get after pre-training with QM9, we can see on average an improvement of 22%, or a decrease in mean average error of 22% compared to the non-pre-trained baseline. And maybe what's also interesting is that, of course, if we pre-train with QM9, or one half of QM9, and then fine-tune on the second half of QM9, which are the mean average errors that we're looking at here, then we're getting the most improvements, because, well, we have similar pre-training and similar fine-tuning molecules. But if we also, for example, pre-train with the much larger molecules, the drug-like molecules of GM drugs, we can see that we're still able to get a very nice improvements with a 20% decrease in mean average error, in mean absolute error on average. Okay. Yeah, I hope most of that was clear, but then maybe let's look at the some other results related to those properties of the QM9 dataset here. And what we have down here in the last row, so we're again looking at the mean average errors when predicting this dataset's properties. And in the last row, we have our 3D Infomax method as pre-training. And here is what we discussed previously, right? If we have a model that generates a distribution of conformers and use that for pre-training, then we transfer the weights of the GNN and use it to predict the properties of QM9, then these are the mean average errors that we achieve. Yeah, and similarly, if we use distances or just predict distances as a pre-training method, this does not work as well as the 3D Infomax method either. And yeah, we can see that we even sometimes do worse than the baseline by using these pre-training methods. I hope it was clear that what the colors should mean. The blue means improvement and the orange ones mean a decrease in performance. Good, but then we have a bunch more properties that we look at, and maybe if you're interested in some non-quantum properties, then we can also get into those. But let me maybe go to what you're specifically interested and have a quick wrap up here before we get into the specific interests questions, so to say. And what we saw now is we can get some pretty nice improvements with this 3D pre-training method and this 3D latent information capturing or generating latent 3D information of molecules. And the representations that we're getting are pretty generalizable, right? We saw that we can have the QM9 molecules for pre-training and QM9 molecules for fine-tuning and get some nice improvements, but we can also get some nice improvements if we use QM9 QM drugs molecules for pre-training that are much larger and drug-like, and then use QM9 molecules for fine-tuning. And then for the future, how could we, or what could some interesting stuff be? Maybe we can look at larger molecules. Is there maybe a way to do this thing for proteins? And yeah, can we get some improvements if we learn a way to generate latent 3D information of proteins? But yeah, as I said at the very beginning, maybe there are more straightforward approaches just to use latent layers of, for example, AlphaFold. Or another idea is that we can maybe combine the 3D pre-training that we propose here with some conventional pre-training methods, like just some self-supervised learning methods on graphs where we do augmentations with, for example, node perturbations. And another idea or another thing that Clemens pointed out in the very beginning, or not in the very beginning, but during the talk, is this preventing us from encoding 2D information in the 3D network, right? We said maybe it's problematic if we're encoding 3D information here. And Professor Bengio pointed out that if we were to actually maximize the mutual information, then this wouldn't be a problem that we're encoding 2D information here with the 3D network, but with our approximation approach, with the contrastive learning, this would actually be a problem, or might be a problem, because maybe our contrastive learning objective can just be solved by distinguishing those the negative samples from the positive samples based on 2D information that we capture. But then, thank you very much for the nice questions so far, and let's maybe get into some more.
Thank you, Hannes, for the presentation. And thanks to everyone for their patience with this Zoom bomber. So now is the time for question. You can ask any question that you want. I might start with the first one. So Hannes, what was the batch size that you used for your experiment, as the number of negative impact the quality of the mutual information that you maximize?
Yes, so the batch size was 512, and do I have the plot here? No, unfortunately not. But yeah, the batch size and therefore the number of negative samples. Oh, here we go.
Okay.
Yeah, the batch size does affect the performance that we're seeing. And what Prudence is saying, if we have a lower batch size, then we have less negative samples here in this thing, right? Here we only have 2 negative samples, and if we because we have a batch size of 3.
Have you tried to kind of as a way to improve the quality of the mutual information, maybe build batch in such a way that molecules that are similar in structure are in the same batch?
No, I wanted to look into that in clustering them by their scaffold and then sampling only from the same cluster of scaffold, but we didn't actually do that. We only looked into clustering or sampling according to the number of atoms.
Okay, cool. Thank you.
Good.
I have a question. This is Avik here. I've been asking some questions. So I was wondering, like the 2D net and the 3D net. So which pairs you are actually maximizing the information, because you on the 3D net you have the atomic distances and which for the conformations. How you are maximizing from the 2D information to that 3D conformation information? So what my question is, which properties actually correlate well with the 3D, which maximizes your whatever algorithm you're designing?
Well, if I'm saying maximizing the mutual information, we just see this. Okay, we just see this latent, or what we're doing is really just this this drawing right here, that we're generating this vector that is now of arbitrary size, right? Like, let's say dimension 256. On here, the same thing, we use this 3D GNN to generate a vector of the size, and we assume that all of the information is captured in there and all of the information is captured in there. So if you were referring to like the problem of relating 2D information to 3D coordinates in some way, then yeah, that's just we use the power of or the flexibility of deep learning to generate vector representations. I'm not sure if that's was what you were asking, but if not, then just bring it up again after we've maybe gotten to Emmanuel.
Yeah. So another question is this information enough to predict various kind of other properties? I mean, whatever data set what you use, it's very different. It's all publicly available, but I would actually ask you to use those quantum property based data sets, which they actually use with Cosmos, to predict the accurate solubility and all. So those data sets are kind of there in the, in the published literature. So maybe use those data sets to predict rather than using the ESOL and all. They are even with the 2D properties, we get better R-square values. Okay, so I would actually ask you, maybe test on those molecules which actually uses this thermodynamics based data sets.
Okay, cool. So yeah, maybe there are some better data sets that we could use to evaluate our method. Yeah, but then let's maybe get to Emmanuel's question real quick.
Thank you, Ernest. So I have a quick question by curiosity. So did you look at the 3D representation that was being learned? Because one thing that you can think about is how different were your conformer and if there's any risk of a 3D representation collapsing. So like all of the different conformer mapping to the same representation.
So maybe let me replay this and you tell me if that's if I'm getting your question correctly. So we might end up just independent, or for this conformer and for this conformer, we might end up just generating the same representation here and the same representation there. Right? Is that the thing?
Yeah, something similar.
Yeah, exactly. Yeah, what we did, for example, was to look at a term that enforces a high variance between the representations coming from the same conformers, and or putting those vectors on a unit sphere, and then having some regularization term on their cosine similarity, such that they have a little bit, or they need to have a little bit of a difference. And yeah, we tried different approaches of avoiding this, but in the end, I'm not so sure how. I can't now clearly remember how the differences looked like, but you can look it up in my thesis.
Thanks.
Okay. Yeah, then Professor Bengio.
So thinking more in the future here, in principle, you could use software implementations that sample conformations in order to do some kind of active learning. I mean, after you've trained the way you've done, if you're given a new molecule, you might sample conformations in the neighborhood or something like this in order to improve the representation and the predictor around those molecules, right? So, and you could be smart about how you query your 3D conformation, whatever dynamics software, so that you improve your network in places where it doesn't do a good job. For example, if finding the relationship between the 2D and the 3D, or in areas where you care more because this is where you want to test or whatever. There are lots of good reasons why you might want to query the 3D computation on the fly, either during training or at test time.
Okay, so is it now during, let's say we want to do this thing during test time, is it what you're saying that we additionally have some other molecules here, or some other conformers that we're generating, and we're putting them also through our 3D network and generating some
Yeah, so I guess you started with the premise that at runtime you don't want to do the expensive molecular dynamics, but I don't know how expensive these things are. You could be, you don't need to do it on everything. You might just be doing it in a selective way. For example, imagine you compute your property prediction, but you also have some sort of error prediction or epistemic uncertainty around it. So you know that you don't have a good prediction. So maybe, well, that's a case where you want to call the 3D molecular dynamics. So how expensive is it to run these simulations, right? So it's something you could play with rather than just working on a fixed data set that you can dynamically call it either at training time or test time.
Yeah, and like this idea maybe especially makes sense if we consider that how long does it really take, this question, because this kind of is answered by it depends on what sort of accuracy you want to have.
Right.
Yeah. Okay.
Okay, that's fine. It was just a comment. Thanks.
Yeah.
Nice talk. Nice work.
Thank you.
Just to give a number, like the data set that we use, the GM drugs data set, they report 6 hours per molecule per CPU. So it's kind of a very, very large number.
Wow, that's really expensive.
Yeah, but that's also if we want to generate very many conformers and with a high accuracy on the probability of each of them occurring in reality. If we just use RDKit to generate like 10 conformers, then this can happen like in a half a second.
Oh, okay. So that becomes playable at test time when you're investigating specific molecules, right?
Yeah. Okay.
One addition is that this depends also on the size of the molecule, the number of rotatable bonds, and,
right.
So, yeah.
So we're talking about drug-like molecules here, right?
Yeah. So the 6 hour figure was for drug-like molecules with an average size of 44 atoms. Okay, but then maybe we have time for a last point by Elena.
Hello, thank you for presenting. I was really excited to see this paper same time as NeurIPS. I have one question for you with regards to split. So from what I saw, you constructed your test set using a random split. Have you tried this using a scaffold split, and do you see similar results?
Yeah, so we actually kind of have a bit more than just a scaffold split if we say that these data sets are completely different. Like here we have this in-distribution situation, right? When we're pre-training with QM9 and then fine-tuning with QM9. But if we're pre-training with GM drugs and have no shared molecules with QM9, and we have just much larger molecules in general, then we're fine-tuning on QM9, we definitely are in different chemical spaces. And similarly, this is the case if we're pre-training with GM drugs, for example, and then fine-tune, or no, if we're pre-training with with QM9 and then fine-tuning on these kinds of data sets. This is not actually what is shown here, because here we're pre-training with GM drugs, which are drug-like molecules. So I guess they might share some similarity with those over here.
Thank you.
Okay, then I want to say a last thank you to all of you for the nice questions and the awesome discussion.